Welcome everybody to today's Tech Talk, the first Tech Talk of the new year. And today Ralf Müller will present a couple of useful but probably less known CDO features. I know Ralf from our common time back at MPIM, where he was a programmer in the old days, and about 3 years ago he joined DKRZ and I followed a bit later. And now he's doing work on CDO and many other aspects of the modeling universe. And so today he'll present these CDO things. As usual, we'll upload a recording of this talk later. And we'd ask everybody to keep their cameras switched off and the microphones muted during the talk. And also during the Q&A, actually, because we'll collect the questions during the talk in a pad document. I'll post a link in the chat in a bit. And you should have already received that link with the invitation. And so if you have any technical questions, you can put them in the chat. Any questions relating to this GoToMeeting thingy. But any CDO related questions go into this pad and we'll just go through them after the talk as usual. If you have any suggestions for future tech talks, please also add these in the Q&A documents. Be it like, hey, I want to give a talk about this cool thing, or be it, I would like to see a talk about something. Just put them in the Q&A document. We have sections for those. And we'll go through them later. Also, if you have any other questions related to the tech talks, please always feel invited to send us an email to DKRZ, so just beratung@dkrz.de, and we'll look into those things. Yeah, with this, I'll hand over to Ralf. The floor is yours. And thanks a lot for giving the talk.
Hello, everyone. As also in the announcement, today I will give a rather short talk. You see, it's only like 17 slides. And let's start with an overview. So this talk should be in 3 parts. The first one will be a detailed review of new or rather new operators in CDO. And then there's a second part, which I present more an overview of some lesser known operators that can be quite useful. And at the last part, we can go through the pad where you can post your questions, or if you have any ideas, I think there will be plenty of room for discussions, and I'm really looking forward to that because input of users has always been a great source of information for developing CDOs and understanding how people use it and what kind of areas and so on. So let's start with a very basic operator called select. It's rather new. There have been a lot of operators for selecting all kinds of stuff, as you can see here in the examples for names, levels, time steps, and yeah, I'm sure you know there are plenty of them. But the point is that the order of these operators can be quite difficult to figure out in terms of performance. So if you just want to know some information rather than like meta information, then it can be quite useful to select only the first time step, for example. But it's not easy to figure out what is the best way. Here you can see 2 examples that should do rather the same thing, but yeah, which one is better? Which one is faster? It's really hard to figure out because it depends on your input data. Number of variables, number of time step, number of levels, basically all the metadata that's in the file. So therefore, the select operator was invented by Uwe, where you can give all these parameters on the same command line, and the operator then does an analysis for you which order is the best one. So as an example, you can see here that you can give multiple parameters like in the examples before in a single command line, and CDO will figure out how to do it. There's also, in terms of performance, kind of a real world scenario, and I think we can have a look at it. I opened it before, so I hope you can see my screen. This was a request about something very similar, actually easier than what I showed before because it's only 2 operators. And you can see here that the runtime can be like quite distinctive. We talk about the factor of 10 here. And just by switching the order. And at the end, I think it was Uwe himself who showed that with a select operator, you get the same operation in far less than even what was the faster version here. It was like 14 seconds, and now we are down to 2 to 3 seconds. So the performance improvement can be really, really good. And as I showed before, you have all kinds of meta information you can use with this operator. So I think it's really a really useful tool to get familiar with and kind of forget about all the other operators. You can stick this one. Okay, the next operator is also an interesting one. It's an operator for doing compression on netcdf files. And not sure if you know about compression of grip files. There it's built into the standard, and netcdf as a file format has kind of a similar approach to do this compression. Of course, it uses an attribute approach on variables, and you can compute an offset and scale factor, which is totally in line with the CF conventions. So if you do this kind of compression, most of the tools will work with that. So it's not a big deal, but it's a lossy compression the same way as the grip compression works. So what it does is these turn your data into 16-bit integer and compute the needed attributes, and you get quite a bunch of compression with it. So it's pretty flexible because you have full control, and you can also combine it with a lossless compression built into netcdf4, which you can use with -z with CDO. Also, this is totally transparent to netcdf, so also these compressed files can be used with other netcdf tools. The only drawback is that it's very memory expensive because for computing an offset and scale factor, you need to know all the data that's in a file or whatever part of the data you selected, with select probably. So you need to read in everything and compute the global range of everything. So it's not variable specific. This is one of the disadvantages of a grip where you have that kind of compression per record. So even below the variable as an item. So it's really one horizontal record that's getting compressed. And of course, the precision you get is dependent on your input range. So for example, I took the topography that is built into CDO, which basically ranges from -10K to +10K, just as a rule of thumb. And I checked the compression rate with different file types, like integer 16, which you see here in the middle row. And you can also go to integer 32 or integer 8-bit. And of course, you get more file compression, like up to a factor of 4. Together with the zip compression, you get even in the range of 6. But the relative difference, which is like the amount of error you get, is also getting higher, of course. As I said, this especially depends on the input range. If you have a smaller input range, then the error is not so severe anymore, like with the default for integer 16-bit. Here, you get like 24% error or up to 100% error if you only choose an 8-bit integer, which, as I said, makes sense if you have a range from minus to plus 10K, then 8-bit integer is really not enough. So the next operator is an interesting one. I hope I remember that correctly. That was an idea from Vera Schemann. She wanted to select something that didn't really fit into a box. So why not having a single point and have a circle around it? And that would be really convenient if you could not only use degrees as the radius, but also other units. And the cell circle operator does exactly that. You can use degrees, radians, and distance in meters or kilometers for describing the area you want to select. So here you can see the example. You just give longitude, latitude, and the radius. Here I also set the length to missing value with a set v range operator. And again, I just use the topography with a certain grid identifier. I will talk about grids a little bit later. And this is how it looks like. So it's a really convenient tool if you have some area and it like fits nicely into a circle or roughly, then cell circles are really a nice option. And as you see, it also works not only with regular gridded data, but also with unstructured grids or like triangular or hexagonal grids like the GME and the Icon grid. It really works well. So if we talk about selection, of course, you can also try to select countries. Usually you would use Salon.box for that and have to check out these boxes. And there are hundreds of these boxes. And I usually do this on a web page, by the way. But that's not really needed anymore because Uwe has included something called the Digital Chart of the World. It's a database, I think, originated from US Defense Department or so. It's from 1992, but it covers the whole globe in that point of time. So maybe there are some political changes until that, but it's like not a big change. But you can use the shortcuts for these countries to compute the box for you. So and even with a collection of countries, it works. Like in my first example here, which you can see on the left, I selected a couple of countries from Europe and used this keyword DCW to indicate that this is a DCW like identifier, and it works really well. On the left side, I used a regular gridded field in the middle, which is the call in the middle. For Germany, I used eigendata. And as a little example, you can try to figure out which country I used for the very right map. There I filled the data with random fields, and there's also a nice feature you can see here at the random operator that you can give a resolution with an underline to the country code. That can be really useful for small countries like this one. You see, it's only 1 degree from in south-north direction and 2 degrees in east-west direction. So it's pretty small, and having the opportunity to set both the region and the resolution of your data set at the same time can be quite useful. Mask region itself, this is just something to remind me, maybe you already know that, but the mask region operator does not cut any kind of data set. It just masks out everything else. So if you select here the mask region Germany, everything else on this map is masked out. The data is still there, or the grid points are still there. If you want to get rid of these points, there's a cell region operator in the 2.0.4 release that was released yesterday. And with that operator, we really get rid of all the cells you did not select. So the outcome is always an unstructured grid, no regular grid anymore. And don't forget to add the bounds to this type of data. with a set grid type operator. Set grid type and the value must be unstructured. Then CDO will try to compute the bounds for you, and then it's a lot easier to work with this data in the future, especially for interpolation or plotting here, like I did it with the Icon data set. So let's to the next one. Yeah, so if we talk about grids, then grids can be quite complicated. I took Icon here as an example because on the one hand, the Icon grid is not a regular grid, and different variables from the Icon model live on different types of grid, essentially different different geometrical elements. Like we talk about triangles, we talk about the edge of the triangle, and the dual grid, which is hexagons or pentagons. And especially for high resolution, this gets additionally complicated because the coordinates are just missing in the output data. Just for saving space, it would be pretty redundant to put the coordinates in every output file again and again and again. With the higher resolution gets, the more disk space you waste. So the approach here is, and I think that's true for most high resolution data sets, you just save the grid file somewhere, and the model data has some kind of identifier, or like maybe only the user knows where to look for the grid, but it's at least in Icon, it's a bit easier because you get these nice identifiers called UUID and also a URI where you can look for the data, but still they're not part of the data set. So what to do? You cannot select anything or do any kind of operations based on coordinates. But what happens if we still do it? Then CDO is smart enough to figure out that the grid is not there, but also where to get the grid. And it downloads the grid for you and stores it like next to your input file. It takes quite amounts of time here, like 830 seconds, but it's a big grid file, so that might be okay. And the next time you do it, CDO recognized that the grid was already downloaded and the whole thing is a lot faster. So this URI information is evaluated by CDO and taken into account, and it does the right thing. But the problem is that should every user download all the files again and again? Probably not. That wouldn't be a really good idea, especially again if we talk about high resolution data. We still have all the redundancy that come with a grid. So CDO offers a couple of environment variables that will help you to deal with that. The first one, the CDO download path, there you can tell CDO where to store this data. Can be quite useful if you work together with other people on the same kind of data using the same grid. Then it's good to put this in a project folder. And you can also try to go for more performance and use something like the temp directory or something similar for that kind of purpose, so that at least the IO part or the time spent in the IO part is minimized. And at DKRZ, these data sets are already stored in the pool directory, as you can see here in the example here. It's in the pool directory. And CDO has an environment variable called CDO icon grids that you can let it point to this icon folder, and then it will try to identify the grid by the UUID or the number of the grids and check for the coordinates there. So you do not have to download anything. It will be handled. And yeah, you see they get of course you get the same processing time as after downloading. So still on grids, for high resolution, or let's say for Icon, The situation with the grid is also a bit complicated because the eigenvariables live on different types of grids, but you also have this grid problem with other models too. So I wanted to take the chance to talk about how the grid information enters CDO. There are basically three ways how this can happen. The first thing is that you have a shortcut for declaring a grid. Like here, the global 1 degree grid, you can just tell CDO to use a grid like this with this global underline 1 or global underline 0.2 would be a 0.2 degree grid. There are a bunch of other shortcuts. You can check these in the documentation on the webpage, like GME or T63 or whatever you want. The next option is that you use text files. Text files can be a good replacement for that. For simple grids, you only need the grid type, like longitude, latitude grids, and some start values for the coordinates, and some increments and the grid size. So when you use the grid des operator on a certain data file, you will know how to write a grid des file yourself. But for grids with unstructured with an unstructured characteristic like icon, it's pretty lengthy because not only the coordinates are just lengthy columns of longitude latitude values, but you also have to provide the bounds, which is an even longer list. So grid des is certainly not an option. CDO, that's why CDO has another option. You can use data files for grid information. And all these options, for example, you can use for remapping or whatever. The CDO is totally transparent to use a grid des file, a shortcut, or a data file. When you use like generation of interpolation weights, then you use the same parameter, and it can be a grid file, a text file, or such a shortcut. The problem is that with some of these grids or grid files or data files, they have not only one grid, but multiple grids. And again, icon is a nice example here because it actually has three grids, one for the cells used for scalars, one for edges used for velocity vectors, for example, and one for vertices used for vorticity. And all these coordinates or grids can occur in a data file. So CDO has to have a default to select the right one, and the obvious default is to take the first one. In this case here, you can see that variables with a cell coordinate called C-long and C-lat, they are identified to have the first grid. So if you use this grid file, you can basically only work on cell variables. But maybe you don't want to, or maybe you have a grid where the edge variables are in the first place. It depends on how the grid file was created. There is no guarantee that the edge variables are in the second place. They could also be in the first place or the third place. You don't know. You have to check it yourself. So in order to be flexible, you have to make sure you know the right ID. So the usual way is that you check your grid file with sinfo or whatever. You check which ID you use. You select this grid by selecting a data variable, for example, or use cell grid with a corresponding ID. But again, you get additional data and so on, basically something you don't want to have. So now you can use, or since a couple of releases actually, you can use the column with the ID to select the grids on the fly. Like in this example, you select the second grid of this icon grid, for example, which, as I showed you before, is the edge grid. And you use these edge coordinates to get connected to the variable Vn, which is the normal velocity of ocean output, for example. And that way you can attach the data variable to the right coordinate variable and finally do some regional selection or conservative interpolation or whatever you want. So no need for intermediate files anymore. You can just use the colon and the right ID, and that's it. So especially for high resolution data, where you don't want to have temporary files, and B, you want to have as much parallel I/O as possible. This is definitely for now the best opportunity to get both of them, because as you hopefully know, these operators they read their input files in parallel. So it's really useful to know the trick to avoid all the problems you have with temporary files. Okay, so much for the grid. The next topic was a bit of a fun for myself. I noticed that there are complex valued operations in CDO, like a Fourier transformation, and also that there are simple operators to work with complex numbers. This is not a very recent addition. This was a bit like limited to certain output formats, but Uwe added the extension of netcdf for complex numbers, which now is a legitimate data type for netcdf. So I thought about what can I do with it? And since we have all the basic stuff there for working with complex numbers in a normal way, I asked myself, couldn't we just generate fractals with CDO? Because actually it's not a complex thing, although it's complex numbers, but they're like for formulas, it's pretty easy. So I give it a shot. So the formula for the Mandelbrot set is in the upper part. It's very simple. And I thought about how to get to the complex numbers in the first place. So I started with writing a grid.des file, as you can see on the left side. From the Mandelbrot set, it's known where the interesting stuff is, and it's on the real interval from -2 to 1, and on the imaginary axis, it's from -1 to 1. So I know that if I start at -2, like x first, and start with -1 at y first, I should be able to cover the interesting area. So I use this with 3 and 2000 grid points along each of the coordinate axes. So I should be able to work in kind of a 6 megapixel image with that. That should at least be in a level of precision where I can see something that looks like a fractal. At least that's what I was hoping. So how to create these these complex numbers? I use the expression operator here. It has some nice features. I will talk about these features a little bit later, but I use the expression to access the longitude and latitudes, basically what I just described in the grid file, to make a data variable out of this longitude and latitude. And longitude has to go into the real part, and latitude has to go into the imaginary part. And then with the rect to complex operator, I can create a real complex data field where the coordinates is the real and the imaginary part of the complex number. So I identify the complex number with its location on the sphere around the 0 point. So the last thing needed was a kind of recursive method to do some computation with this complex number. And this is how it looks like. I used Ruby here, but I think it's pretty obvious what I did. I use the add operator for the plus, obviously, and the mul operator for the multiplication with itself. So the recursion works in a way that for 0 or 1, the complex number is returned, as it's also the case for the Mandelbrot set, of course. And otherwise, I compute as follows. I just take I multiply my input field with itself, and I add the constant, which is my basic input. And the rest is just for cosmetics, that I stick to netcdf4 and that I have a certain output file name so that I can identify and reuse my output for other purpose like plotting. But it's just a very simple recursive function. So, and what I got was this. So pretty much what I imagined. I was that really made me curious what happens inside the Mandelbrot set. So the problem here is if you look at the absolute value of these complex numbers, after a few iterations, they really exceed the whole double range in that file. So there are no chance to have more detail like a black and white image, as you can see here. So the next step was to limit the operation of the square or of this series of the Mandelbrot function to the range where the plot can generate some nice colors. So what happens inside? I thought about writing a limiter, and the limiter is actually pretty easy. The main part here is in the amplitude for the complex number, and I just limit the amplitude so that the multiplication operation does not exceed the values so much. So what I did was I compute the absolute value, then I do the first mass where I limit this value to a certain range, which I decided was 5, because the Mandelbrot set is usually with a limit of 2. So I wanted to be a little bit above that, but not too much. So I compute a 0-1 mask where 1 is okay and 0 is the stuff that should go away for later multiplication. And I also computed a negative mask with a greater than constant where I have a 0 area, which is okay because I use it with an addition operator, not with multiplication, and something that is a 1 on the outside world that and this one I can lift to 5 with the simple multiplication with a constant. So I get rid of all the data that exceeds a range more than 10, for example, because that would destroy my later plotting. And then I have this real valued mask. I compute the imaginary and real part. I apply this mask as I said here with a multiplication and then with an addition. And then I create a new complex number out of the old one, basically. So I throw away everything where this limit is exceeded, and when you go back, I just have a new recursive function where I do not call CDO on the data, but I call CDO, and I put this input into the limiter, and then I compute the next Mandel set, so to say. So it's very easy. You just apply the limiter before you return the field. That's all. And this is what I got. So I could have a look into it. You see here in the upper left corner, this is the plain complex field limited to the range of 2. Like we are at 2 degrees west, so yellow is like close to 2. And this is the second iteration, the third and the fourth iteration, and so on until to the iteration number 20. So it's really nice to to be able to look into it. And yeah, it was a nice exercise to see that you can basically do some beautiful stuff on complex numbers, even with a tool like CDO. Okay, this is the last part where I collected some operators really worth keeping in mind. Or the first one is bottom value or top value. This might be a lot more interesting for ocean developers because they have the problem of vertical boundaries. So here, bottom value is a very it's worth knowing that this operator exists, because otherwise you do a lot of computations not needed if you know this. Then there's a verified grid operator. This is pretty useful to inspect the data files or the grid files you have, because it will tell you about the bounds, the coordinates, if they are the coordinates that are used multiple times and so on. So it can be really useful to get more information about the underlying coordinate structure. And then as a real classic, there's the expression operator. It's very powerful. I only selected the coordinate functions here. There are a lot more functions, especially related to numeric operators, like field mean, for example. It's not only a CDO operator, you can also use it in the expression operator itself. But here I wanted to concentrate on the coordinates, because on the one hand, I used C-long and C-lat before, but also the latest addition is the C delta Z operator. That's quite useful to if you want to compute kind of an integral of your 3D field. But also when it comes to time information, it can be very useful, because time is not a CF conform data variable. So it's hard to save a time value as a real time. We'll always have to save it more in a form of an float or integer number, and expression has all the stuff you can think about. So it's really worth knowing that it's there and it's very flexible. So then we have skewness and kurtosis. This was an idea from Diane in her ensemble analysis. These higher order moments, they are there in many areas, like for fields, for ensembles, for zonals and meridionals. And the same is true for the median in all these dimensions. You can have a median analysis, like in a horizontal median for one field or a zonal median. It's all there. You do not have to think about which percentile to use and how to write this percentile down to get your median. So it's just a simple operator, or a bunch of operators right now. Okay, this is the end of my talk. Thank you for your attention. And yeah, just as a side note, I stick to the PsyPlot tool by Philipp Sommer. I wanted to try it out myself, and all the plots here are done with it. Then there's a short link to the FAQ and the operator news that might be worth looking at. The FAQ by Karin, one of my colleagues, is a pretty useful source of information, especially for beginners. And the operator news is something like worth looking into, because there's more space to have more examples, some plots, and to understand these operators. Then it's really also quite useful, I think. At least I hope so. So thank you for your attention, and the floor is open for going through your questions. Thank you.